Good afternoon, ladies and gentlemen. We are Group 1, and this is our math presentation. I'm Dean. You all know Antoine, you know Kevin, and you know John. First, John is going to tell us a little bit about the problem that we are chosen to do.
Okay, so let's jump right in. So here in this figure below, we see that the interior region R consists of all the points inside the square that are closer to the center than to the sides of the square. Hence, the border of R consists of all the points equidistant from the center to the sides. Therefore, we need to find the area of R. And now, Dean is going to give us some background information on parabolas and how we can use them to approach the problem.
Parabolas in this problem go hand in hand. According to our math book, a parabola can be defined as a set of points on a plane which are equidistant on either side of the point from the focus from a fixed line. So if we take a look at the problem and what it's asking, what we really can tell is that we're just asking to identify a series of parabolas and figure out the area inside of them. So this is a really confusing looking Desmo simulation that I made that bears striking resemblance to the shape that we've been trying to figure out as per the project problem. So this area right here, the intersection of all four parabolas, where they meet, right, the area inside of that is the area that we have been asked to find. So our focus for all four of those parabolas is this point right here in the middle, and our directrices are the lines that make up the square. Now that means that the length L of the square goes from one directrix to the other, and we can say that the focus of our parabola lies right between, that is, 1/2 L in each direction. So this is a general parabolic equation. This is again taken directly from our book. X squared equals 4py, whereas the focus is at 0, p, and the directrix has the formula -p. I know this is a lot of mumbo jumbo, but again, all we have to remember is that because that p is right between the focus and the directrix, it is 1/4 of L. Now, if you try to graph these equations, you'll notice that there's a little bit of a problem because that these equations, this x squared equals 4py, makes it so that the focus of the parabola, or not the focus, but the vertex of the parabola is at the origin. And that is simply not true in our case. So we need to add a constant to these values to change the vertex to halfway between the center and the edge, just like it is in our project problem. Now, this was crazy, and after a lot of modeling, I happened to figure out that the distance, the constant that you add to get that parabola to shift either left, right, up, or down happens to be c over 4p. So because that we wanted c over 4p to be 1/4 of the distance of L, we were able to say that c over 4p equals L over 4. Because we know p in terms of L, c over L equals L over 4. And then finally, we were able to conclude the constant we need to move the parabola is L squared over 4. And now Kevin is going to tell us about how we can use symmetry to solve this a lot easier.
Really wish there was more feedback on here. Due to symmetry, we only need to search for the areas of 1/4 of this. Then at the very end of it, we'll be able to simply multiply by 4. So instead of having to get something for all of that, all we really need to do, due to symmetry, is find the area of this, which will be made up of two integrals, one between here and here, the other one between here and here.
Try clicking slide number 6 and then pressing the down button. Yeah.
Oh, the computer.
And did you delete everything after 6?
How can I possibly do that?
I have no idea.
Click undo.
Well, there's.
You did.
No, it is. Well, that's my slide, right? By pressing down on the keypad,
I
you
have
can
no
slide.
idea, but.
I'm sorry, we happen to have some technical difficulties. This is resolved, and now we will go back to Antoine talking about our method of integration. Oh, but we also are missing a different slide between 6 and 7. Try pressing it.
Click undo.
There we are.
Okay. Problem resolved.
Okay, now we're going to be talking about parabolic equations. We basically set up where we have found out that the top parabola is actually going to be x squared equals L minus y plus L squared over 4, as well as similarly the parabola from the right is actually going to be y squared minus Lx plus L squared over 4. So here's the picture of it right here. Right there is actually the intersection of it, and just as Kevin has said, we're going to be integrating from right here to right here. And remember that this is the right parabola, that's the top parabola, that's where they intersect, and we're going to integrate basically horizontally. Now, right here is actually where all the work is actually being done. Whereas you can see where we had ended up coming up with the side one being y equals square root of L negative Lx over L squared, and the top one actually coming out to y equals L squared minus 4x squared over 4L. Now, we're going to give it right back to Dean for him to take it on home, basically.
Okay, so having that information that we needed, here again, able to integrate from left to right. So here is that first parabola, that is the top parabola, is the equation here, and we're integrating that from 0, which is where it starts, to this point, L over 2 root 2 minus L over 2. That's the point that we algebraically found to be the point of intersection between these two parabolas. And then we do the same thing, but here with the parabola on the right, and we start it at that point and end it at L over 4, which is the vertex of the parabola. As Kevin said, we use symmetry, so we're simply going to multiply this by 4, and then it will give us the total of all 4 quadrants, not only the one that we integrated. So, in short, with this presentation, we have started with a crazy problem, and we learned some very, very intimate things about parabolas, and then put that knowledge to the test when we created our very own parabolic equations to integrate in order to give us this beautiful final equation. Now, this beautiful final equation cannot really be evaluated. We had to leave it as an integral because not only is the integral very elaborate, that is our f of x, and difficult to integrate, but also you'll notice there's actually 2 variables in here. We have the variable x, and we also have the variable L, which carries from the beginning. Because that the original problem did not specify for us at times an area within the shape for a specific value of L, we had to find something a little bit more general. Thank you.